Galactic, bringing you another presentation in cosmic science, which does cover both the tiniest things, such as photons, and the largest thing, which would be the universe. And anything in between, which would be at various scales. Macro scale, cosmic macro scale. It's relative, isn't it? You get down to the size of a BB, an ant, a molecule, an atom, a proton. Well, we tried to understand the atomic system. And there's a reason for that that does have to do with astronomy, which is how I began. But not in producing on YouTube, which was with a mathematical discovery. So today we're going to go over again, that is, I've made presentations on this subject before, but it never hurts to repeat. This should be more of a summary. I was still working out the ins and outs of the mathematics, which seemed quite simple at first. And it remains simple, and I should explain what I'm talking about. I appear to have run across a geometric construction, which is quite simple. It's the sphere. So we all know what the sphere is conceptually. It's remarkable to be able to say that it is possible to parameterize spheric space, which actually shouldn't be too surprising. And in fact, it has been done in various mathematical contexts. The current reigning model is the Riemann sphere, which, believe it or not, is composed on a two-component number system. You have heard of it, but it's interesting to be able to make statements such as I just made, that the Riemann sphere, which defines spherical space for very much of science, it's not the only sphere. There's something called the Bloch sphere, and there are various spheric models because, for instance, the atom is a spherical system. So is a star, and so is the Earth. So we do encounter the sphere at very many levels. I even made a case, although this is not nearly as clear, I would say, that the universe appears to us to be spherical, but that is more of an incomplete statement. The Earth definitely is spherical. That is, planets are. And we do have a model for explaining why that would be that seems to me to be pretty much the most obvious guess. But it would be a guess. And really, to come up with a theory of planetary sphericity, that is how planets form, it's got to be some kind of nebular or globular hypothesis that would come first to mind, that has come first to mind, and has stuck. That theory has been around a long time. Where stars come from took a longer time to get anywhere near what we now know is a much more accurate statement, because no one really knew where stars came from until we could analyze at least what stars are made of, which is a remarkable thing to be able to say that we did discover what stars are made of by reading the light. And we've also made a big, huge case in our quantum explorations about the fact that light carries such an astonishing amount of information. I won't go into detail here, but spectroscopy largely covers that, although that's not the only. We do see colors, and that but distant objects, of course, that becomes more difficult. Now, all of this is to say that we do see spherical geometry in the universe. Now, it really was only in the 20th century that these discoveries of, for instance, galaxies have a spherical characteristic. That is, even the spiral galaxies are circular. And that is properly a proper enough way to say it. A spiral is not a circle, but they're on. It's a planar object that's actually a flattened sphere, and it turns out that even spiral galaxies have a spherical aspect, as you might guess, because the easiest way to explain why a spiral galaxy is a disk, really like, well, I was going to say frisbee, but more like a pancake. And the bulge is in the middle. So it attenuates kind of like a flying saucer. In other words, it's much more spherical towards the center. Now that comprises only 45% of the large galaxies, what we would ordinarily call galaxies. There is a whole train of smaller galaxies, and Fritz Zwicky was the first who made his comments, really discoveries, about the nature of smaller galaxies, smaller than the Milky Way and Andromeda, which are comparable size, although Andromeda has actually been measured rather reliably, we think very reliably now, in the 21st century. It's slightly larger than our Milky Way galaxy, which I am misnaming. Although not really. Colloquially, you could still refer to our galaxy as the Milky Way galaxy. It is certainly done in hundreds of books. However, it does have a name. The Milky Way originally was our view of the galaxy from the inside. In other words, it's a band of light. That's why it's called Milky. Because if you've seen the galaxy in the sky, which you would have to see on a very clear night, of course, but you're able to travel and wait through to the right season and the right day, really the right night, you can see the galaxy. I like to emphasize that you always have that possibility, but there may be distance and time considerations. But it does appear regularly, very regularly in some places, and it looks like a band of milk because you can't tell that it's stars. So, hence the name Milky Way, and really the name that we use when looking at it from the outside, it has a name among the galaxies. You see, we're seeing it from the inside when we name it the Milky Way. But is that really its name? Well, of course, this is a matter of pure subjectivity, but it's delightful. I mean, it is its name. It's our home. Really, the same way that our solar system is our home. So there are other planets, but only one Earth. Well, there's a lot of galaxies, but perhaps there's only one. Well, what is its name? Via Lactea. Now, the irony, and I purposely said the R, although you actually shouldn't. The irony of that is that Via Lactea, as you may already know, is Latin for Milky Way. But the reason I know that, and I'm laughing out of familiarity with that irony, is that I've written catalogues of galaxies. I've cataloged. My largest catalog of galaxies was, I'm going to say 50,000 galaxies. And that is called the PGA, whose actual meaning of those letters in that acronym, for some reason, I can never remember what that P stands for. This happened. Have you ever had that? You have just one word or one name, and you remember anything else that's like it, but this one name, like some actor, I'm that way with. Oh no, I gotta try to remember his name. And then you have to describe. I can't remember his name. Tom Hanks. For some reason. So what was it I was trying to remember? Okay. Well, that's enough levity. Today we want to get serious, and I've already used up 9 minutes. But that was to transition, because we're now transitioning to a new series, which I'm going to try to condense down to just this one presentation, but that hasn't happened yet. Now, the reason for that is this project has grown. That is, this discovery has led to other discoveries. I'm still on a discovery vector even after 2 years. And believe you me, I am just as surprised, I think, as anyone else would be, but rather lonely. Science is communicative. You want to share your ideas with somebody? Well, let me share my idea with you. Maybe you'll like it. I certainly do, but I can't fact, but this is actually the foundation of everything that we've gained, our insights into quantum mechanics and space-time. I should have to say, I'm attempting to cause you to understand those two things. Well, I'm sure that I've at least made some progress on your behalf. I knew nothing of quantum mechanics. Well, it's been 7 years now. But 7 years ago, I knew nothing of quantum mechanics, so that's... But I have been studying it ever since, and increasingly so. And I do work every day. And I have been for really 3 years. But I've only been producing on YouTube for 2 years. So there's our full bracketing information on what began with what I'm going to tell you now. So empty your mind and get ready to learn mathematics all over again from the ground up. None of this will scare you. In fact, I'm sure you're going to be very pleased. Now in your mind, draw a line. Just remind you of grade school. I mean, you even put a blackboard there if you want, but I would prefer that you didn't, because of my next question. A couple of questions I want to ask you about that line that you just drew. First of all, I'm just going to axiomatize things so not to torture you with questions. I'm not trying to test you or quiz you. But I would like you to understand that this is actually a difficult step, is to begin. So where did you draw that line? Well, I'm just going to say we're drawing it in a metaspace. And that metaspace is in the mind. So that's really quite simple. And you hardly need to say that. Oh, no. You need to say everything at the axiomatic basis, because everything else proceeds from that. Now, it turns out this metaspace, we're not going to need it. Shortly, we're going to discard it, because we're going to have a geometry of space, which will exfoliate into something much more magnificent. It turns into space-time, but correctly, so that it matches physics. Now, what we've done, just so you know, this is not a hocus-pocus sort of thing. When you create a geometry, for instance, 3D, you've heard of 3D, well, that's 3 lines. That's what 3D is. So it's a grid. Now, you can see there's also such thing as curvature. What's the simplest curve? It's a circle. We see the moon as a circle. We see the sun as a circle. I've said this many times in prior presentations, but I always mention, but you don't want to look at the disk of the sun for very long. It's okay to look at the sun for a second. Now, there's a difference of opinion on that, by the way. Because of differences in eyeballs from human to human, there are variations. And age. And other things, like how bright is that freaking sun, because it's measurably brighter at certain times of the year. So, don't look at the sun without protection. And even with protection, don't stare at it. Now, there's a whole branch of astronomy where they stare right at that thing, but it's a cool, nice, because they have a filter. So you can look at the sun through a telescope, but not without... Don't ever try to do that. Well, people have in the past, but I would assume, well, you never know. Maybe there's a report that can be consulted. It says how many people or kids or whoever, dum-dums, you don't want to say that if they burned their eye out. Well, the worst thing you could do if you really want to hurt yourself badly is get a pair of binoculars and just glare at the noonday sun. You'll burn your retinas out in no time and go blind. Very easy, just like burning ants. That's what you're doing, is focusing. So starlight, don't worry, will never hurt your eyes. But actually moonlight with a powerful telescope is known. There are definite warnings if you stare. And I love to do this, so I'm aware of this acutely, because I like to just look at the moon, not the sun, sorry, the moon, through a telescope. But on a full moon, it's actually slightly dangerous, depending on the magnification and all those other factors. So I'm required to say that as a conscientious astronomer. And this is an astronomy channel. We got into quantum mechanics because we have to know about the flight of the photon for fairly obvious reasons if the whole purpose of this channel is to help the layman understand cutting-edge physics. Well, a lot of people are doing that. Well, so am I. But not in a way that you've ever heard before, because it's all based on a different geometry than is used in... Now, here's where they meet, and this is a good way to begin. We do use the 3D grid system. Hey, Albert Einstein used it, okay? And I don't want to go into that little thing, but Albert Einstein, yes, used a geometry, 3D geometry. Of course, he extended it. He added a fourth orthogonal line in imaginary space and called it time. So I've given several presentations and presentation series on just how amazing that is. It involves the orthogonality of time with space. And you and I, if you followed, but I am going to summarize that, but we have to, this time with the mathematics. So this would frighten me, except I know that this is actually easier. So let's begin with our straight line, which is in metaspace, which is in your mind. Okay? That is, none of this is strange. But it is important to know what we're doing, because this is basically starting over one step before Euclid. Now this step sure sounds like Euclid. It's not. This is not Euclidean yet. Just because we just drew a straight line, that doesn't mean it's Euclidean. That word is very interesting. It has to do with orthogonality and parallelity. And that's actually how you say it. Parallelity. 3 L sounds in a row. Parallelity. Parallelity and orthogonality. That's right angle and straight. Straight from 0. Right? So that's called 180 degree valence. Because plus minus is 180 degree valence on a metricized line. Even that's not Euclidean. In fact, here's how Euclid began. It's not his first statement. I've given a presentation on Euclid's first statements. The first one has to do with the nature of a point. And it turns out that is the right way to start, but he has an idea in mind. Now, we're not starting with a point. So already, this is a non-Euclidean beginning. Although, that's not quite fair to Euclid, because what he was driving at, he was setting up for the line, which is his second statement. That a point has no dimension. It's really what he said, although he didn't use the word dimension. We do. And that is exactly what Euclid meant, that the point has it's 0D. And that is Euclidean. If you start with a point and say it's 0D, that's a systematic, also called an axiomatic basis. And I've given presentations on that, because an axiomatic basis implies a recursion. And it can even be more than one recursion, depending on what you're trying to define. In other words, as I stated earlier, it's hard to begin because of that recursion. Now, we artificially cut it off at metaspace inside the mind. That's our beginning space, but we haven't defined it except in this way, that it's a space in the perceptual space of a human mind where you can draw a line and see it. Well, are you fooling yourself? You see, it is recursive. You have to prove everything you say, no matter how obvious it is. But we can stop there. The answer to that question is yes. So that's my choice for how to begin this axiomatic basis, which is non-Euclidean for the reason I just gave, but it wasn't quite fair. Because Euclid began by saying a point is 0D so that he could define 1D. And so his second statement, in Elements, that most famous of all books, tied with the Bible, I think it's fair to just put it that way, because nothing else is even close. It's the Bible and Euclid. for the two leaders among, and you'd have to look it up. And again, that's not really to the point, but it's interesting, isn't it? That the first sentence in that tied for most famous book of all time is the definition of 0D as a point, in order to get to statement 2, which is that a line has length but no breadth. Nobody's ever been able to come up with a better... You can state that in many ways, and it has been stated in many ways, but that is always equivalent to what is just stated there. So that is a Euclidean line. I haven't said what he said, though. That's his first statement about the line. But he doesn't... You see, that all that says is that it has length but not breadth. Well, that's a pretty good definition of a line, but it doesn't say anything about it except that it's obvious what he's saying, because we know what length is. So he's defining the line by length. And now I think you can see why it's so important to state even what maybe seem... See, if it's obvious, then it's tedious. I hope you didn't find that tedious, because we're going to begin... You could say we begin the same way Euclid began with his second statement. We're not beginning with a point. He did begin with a point, and the reason is he's going to need the point in order to define the line the way he wishes to define it, which is what again? Length. And length cannot be infinite. Infinite is not a length. It's an abstract concept that is strongly related to the length. You could say you have to decide that. Is it infinite or not? We're going to get to that, actually. That is an important distinction. Now, the way Euclid began was with a point so that he could have two endpoints. And of course, that's called a line segment. However, the line segment is implied in an axial system, even if it's a single axis. That's a one dimension. That's where we get our numbers. Our numbers are called linear numbers for that reason. All of the numbers that we were taught in school, all of them, even the transcendental numbers. You do have to halt, though. There is a footnote. Not the complex numbers. That's an invention. Of course, it's exclusively used now in upper echelon physics. Exclusively used. I mentioned earlier that the current reigning, definitely leading champ among the spherical constructions, all of which are linear. So, that's a superposition, right? Oh, yeah. That word may ring a bell, superposition. What are you superposing? The right question is, what are you superposing on? And even better, what are you superposing in? Superposition, super means layered. It's a two-layer. That's what superposition always means. Two. There are two that are layered. So that actually is not binary, because it's both. Electromagnetism falls into that category because electricity never occurs without magnetism. The inverse is more difficult to prove, but it can be proved. So that's called electromagnetism for that reason. So you see, the axiomatic basis can be extremely important. Now, in the case of the straight line, I argue that we were blueprinted to see that. I don't see how that could be argued, although it does carry a connotation that's philosophical. Because blueprinted it invokes the concept of design. Well, there would have to be some kind of design. And really, any argumentation about that aspect of us discovering the line, like, was that a coincidence? For me to say that it's blueprinted, that we were destined to see that, because men have always known about length. We've always been able to draw that straight line on the ground as if it were dead straight. We've always known that. To the beginning of recorded history, men have known what a straight line is and what it's good for. Very well established. But that is the basis of our linear number system, which is quite miraculous. Nobody can deny that. Although there's a long story about how we developed the linear number system, which you and I were taught in school. But you see, there is a one-to-one correspondence so far with the concept of the numbers, which are all on that by the way has been proved, is that all the numbers e, pi. Now what about I? Yeah, it's still on the line, because it's, instead of the square root of 1, it's the square root of -1. That's on the line. Where is it then? What is the square root of -1? Where would it be on the line? Well, actually, it's not on the line. I kind of fibbed. You can make it go into the line, but in order to do so, you have to develop complex numbers, which are two-component numbers. And that is one of the most interesting geometric tricks of all time. And I have several presentations covering that, and we're going to actually explore that, but only as a very temporary turnout on our scenic drive. This is not going to be challenging, except conceptually, it could challenge you because of what you already know. So one of my first tasks in presenting this mathematical sequence, now that I've had some practice doing this, in my own mind, complex numbers always come up. And I've had to wonder in my own mind, is this appropriate to present if you're attempting to establish an axiomatic basis? Here's why. It's because it's a two-component number system that works and has enormous value for a reason which can be defined, and I know very well. Why complex numbers? You see, it makes a space. It makes a two-dimensional space. That can be extended to 3D, in which case you could complexify 3D by adding another axis. Essentially, Einstein did that. The I does not appear in the standard formulation of the equation of general relativity, called the Einstein field equation, because it describes gravitational space. Well, that's a 4-line system. Well, it's very interesting, because it's trying to model spherical space with an enormous overhead of calculus, and it's actually, I call it hypercalculus, and I'm definitely justified in inventing that name with a prefix. It's not ordinary calculus in the sense of its level of complexity, and I've given presentations on that with reference to a YouTube presenter who taught me, and I had to watch his 3-hour video series twice. The first time I thought I got it, only the second time was I sure that I got what is. It's very hard to even explain. That's why it took, and it's extraordinary. Leonard Susskind takes much longer to explain it, but for reasons which make sense. In other words, it's not that Leonard is being either lazy or too many words. But for someone who's trying to understand space-time, that is space-time. It is the general relativity equation called the Einstein field equation for gravity. That is space-time. So, that is a linear system measuring a spherical phenomenon called gravity. Gravity, everyone knows, is spherical. So, interesting. Now, what we're doing is not beginning with Euclid's line. It has been stated, and I've checked this in several sources, Einsteinian space, in one sense, it's an important sense, although there's a bit of debate about this, is Einsteinian space Euclidean. The base system is, 3D is Euclidean. But with the addition of his fourth orthogonal axis, he actually added something else, which is an algebraic, basically an algebraic conversion system, totally reliant on calculus, but not only on calculus. And that's to get at curvature. That is what calculus is for, and I've given several presentations on that. So you see how quickly this complexifies, but in a good way. So, now we get into the mathematics, but in order to get into the mathematics, we begin the way Euclid began, which was not with mathematics. Mathematics is based on geometry. That has been proved, so you can accept that. And in fact, I already stated so. You can attribute that discovery to John Horton Conway. And I'm one of the few people, I think perhaps the only one, I may have read this once, but from several sources that I've consulted, among mathematicians attempting to explain in some way John Horton Conway's surreal number system, surreal numbers system. It's actually a binary tree showing the correct relationship between all the numbers, beginning at 0 and ending at an infinity of infinities. In a sense, completing Cantor's work. But in so doing, John Horton Conway had to come up with an axiomatic basis, and it's unbelievable. And I am apparently one of the only men to both notice it. I can't even believe that I'm the only one to have noticed that he defined the linear numbers for the first time correctly. But as he did so in his binary tree, generating all the linear numbers, which is all of them, he uncovered the radical axiomatic basis of a second number system. It's very interesting, and I have several presentations on that. So here now we're going to start again, empty your mind, and draw a line. We have not said anything about points, but we're going to say something about points now. How did you draw that line? You see what I'm doing. I'm separating from a center point. It can be proved that that's how you draw a line. That is what a line is. And we can thank Archimedes for that insight. And here's how you can get the Archimedean balance principle onto such a simple thing as a line and empty space in your mind. Does that line have any characteristics? It has the Euclidean characteristic that it's straight, but that's really obvious, so that's not saying anything. Does the straight line have any characteristics? One very obvious one. That it runs off in two opposite directions. Correct? So this matter of 1D has a hole in it. And that hole is infinity. That when you draw that line, it doesn't end, but very importantly, it doesn't end in two equivalent directions. That's been substantiated in astronomical physics, often abbreviated to astrophysics, that any straight line you draw away from the Earth is equivalent in all directions. Well, if so, that is a spherical direction, correct? We're going to capitalize on that insight in just a moment, but we're not ready for it yet. But we're very close to being ready for that insight. All we have is an empty line that is, it has no numbers on it. It has no points on it. It has to have two. Plus infinity and minus infinity. Now we haven't said that those are numbers. We are saying, though, that they're points. It's just that we don't know how far out they are. But that line definitely has 2 points. And that is Euclidean. So now we've caught up with Euclid, but through Archimedes. And this is the right way to get to Euclid, is through the Archimedean balance on the two infinities. I've given that a name because apparently I'm the first person to state this explicitly, is that when you draw that line, in the empty blackboard of your perceptual space in your mind, that perceptual space is spherical. And here's why. Is that line a single object? Yes. So as such, does the single object touch anything else? Yes. Infinity. But you have to add something. The number 2. I've given a series just within the past 2 weeks on the number 2. About 4 hours. Well, a big fraction of 4 hours. 4 presentations over a period of days. On the number 2. Just covering where it occurs in significant places. Well, here's perhaps the most significant of all. That the Euclidean line we can define inversely to the way that Euclid began, and he began with a point, because he knew he was going to need it in order to cut the line off on 2 sides, to make a line segment, because that alone is length. The distance from infinity to infinity is undefined, because you can't cut it at infinity because of a paradox. And I'm going to show you the solution to that paradox, but we have to get to it step by step. This is the right way to begin. Euclid began correctly insofar as he started us out with a line. But the way he defined it really didn't matter for the primary purpose of the line, which we now know. It was to get us the linear numbers. Because the line and the linear number system, well, not the linear number system, the linear dimension is the line. And that dimension is where all the numbers are. You can make a grid by making 2 of those orthogonal, because the 2 lines are related in a way that we can define mathematically, and you can see it's based on geometry. But the line itself, without any other lines, not 2 and not 3, or even 4 for spacetime, but just 1, which can be oriented in any direction, correct? That's another way of saying that the center remains fixed. So if you extend out from the point with a line through spherical space, you could begin that way and say that it has an endpoint. And that would be a sphere. Correct? So the center would be the center of that sphere. And that's the integral of all the lines. These would be line segments that intersect at the center, but in spheric space. Now, we don't want to do that yet. I'm going to prove to you how we can get to that by beginning the way we began, which was how? We now have a center. We also have a dual edge, and we haven't cut the line, but we do have a point. And that's our first definition of the point. I said that it appears as though the line has 2 points, but they're at infinity, and we're not going to say that those are points. We're only going to say that the line has 2 ends, and not say that it's a point. Now, in projective geometry, you do say that it's a point, and that is one of the most amazing geometries in the history of human civilization. It drove an entire change in art due to the use of perspective, and that's actually projective geometry with a point at infinity. That can be done. It's highly specialized, though, and I just wanted to point out to you that this line and the concept of the point can be manipulated. Now, when you have a distance, you must have 2 endpoints, and this is how Euclid defined the point. We are not defining it that way. The point is not defined except in one position, the center. And that's the beginning of spherical space, but to prove that we can do that, we begin again, draw a straight line. We'll say that's redundant, that when you say line, you mean a straight line, as opposed to a curved line. So this is a line. As science, nobody argues with this. Now, the extension of the line is well enough defined that we are confident that we can create a segment. It's of arbitrary length. So now you need a metric. And this is what we've done. It's called a ruler. It's the difference between a straight edge, which you can find the center by balancing it on your finger. If you take your two, you know this. If you take your two fingers and put them under a ruler and push your fingers together, where your two fingers meet, that ruler will be at its balance point, and then you can actually balance it on one finger. We've covered that paradox too very recently. That's a very interesting paradox. You actually have to maintain it by using hand-eye coordination. It won't stay there if you can't see it or detect its micro motions. This would be as if you had a perfect pin. Actually, the tip of a perfect cone was your finger. How long would a sphere stay balanced on top? It wouldn't. But geometrically, you can prove that it might. That's the same thing with infinity. So we're not going to define it. We don't need to. Euclid did not. Although he drove at it with the concept of parallelity, and that's the most debated. It's even debated what it should be called. I won't go into that, but I've given presentations on that. So we've begun with a line that has a center, and we're going to say that that's a point. And now we're going to use a theorem that I developed called the antipodal theorem, based on the two infinities which have a geometry. This is plus infinity over here and minus infinity over here. Well, okay, good. How far are they from the center? They're equidistant. There's no difference between plus and minus. These are opposite rays. Now, that means that we have a center. So we're going to say that is the center. Since that is a center, you can draw from that point a line segment in either direction. Now that should be obvious. So that is Euclidean geometry when you do that. So that's Euclidean geometry. That's all it is. It's involved with being able to make a distance segment on the open line. That is the correct way to say that. This line that we just drew in our mind, that's an open line. But Euclidean space is not based on the open line. It's based on a closed line that must, in order to have a metric of distance, must have 0 at one of the termini. And so this is called a ray, and that's taught to us in school. It connotes a sun ray in a certain sense, but that's misleading. So it's not a ray in the sense of a ray of light. It's simply a segment that's half open. Half open, because you're going from 0 and ignoring negative space. So really, Euclid was not really ever talking about negative space. Those numbers were not even invented in the days of Euclid. There was no such thing as negative numbers. I believe you can verify that rather easily. Probably just in Wikipedia, a couple of lookups, and you'll be able to verify that that is true. That's not what we're doing. We have a completely different definition of the point. But the line, we haven't done, it's the same line. The line is the line, whether you cut it or not. But if it's just a line, it's an open line. But you could also say it's a doubly open line. And that's the best way to say it, because you're giving the most amount of information. It's a doubly open line. There's also such a thing as a singly open line. We call that a ray, but you can see it has a more precise name. Not better. They're equivalent names. It's a single open line. Now, once you have a distance, you have a closed line. It's a 0 open line. It's it is not open. I don't need to belabor that. So that's why the line is an interesting thing to define in this sense. That even when there's only one point, you can still define it as doubly open from the point, singly open from the point, and now you have to say something else if you're going to be fully complete. It can be singly open in one of two directions, and that's plus minus. That's geometric, from the point, for the line. And that's called the metric of the space. That is called a geometric space. We call it 1D. Euclid had an equivalent description for his line. So that is the line we have. It has a center, and it's doubly open. What does it mean that it's doubly open? It means that it hits two infinities, but these are linear infinities, and if it actually hit either, well, it would be both because they're equivalent. If it hits both infinities equivalently, it would do so as a what? In each case, it would be a point. But if you're saying where does the line intersect infinity, you could say that it's at one surface, and if you do that, you define the sphere. That this line that goes to infinity goes to an unbounded spherical surface. Right? Now the interesting thing is you can see immediately that that opens up what's called a degree of freedom. And it turns out there's just one degree of freedom. Now, for the line to go out, that is a degree of freedom, but you can see it splits from the center. So that is the nature of the degree of freedom from the point. Linearly. A single line extends equivalently on a 180-degree valence in free space. But we can prove we don't have to say free space. We can say spherical space. And the reason is, since those two infinities are equivalent, and the line itself is arbitrary with respect to where it hits in two places, that implies, technically, that is the integral of the ray. That is the integral of the semi-open line. The surface is. Correct? That would be a spheric distance. And you can metricize that. You can go out 1. The same way you go 1 on a line from 0 to 1 is a distance. This is a distance from the center to the surface of a sphere. And that distance is 1. Now you may say, that's pretty obvious, but why has nobody ever tried that? And you may be trying to answer that question yourself. This would follow a natural course of logic, in my opinion, is that there is no possible reason to do that. Yes, there is. Yes, there is a very good reason to do that. An extremely good reason to do that. So we're going through this step by step. But actually the hairs on my arms are standing up right now. Because that is an incredible difference in the metricization of space. That instead of going from 0 to 1 on a straight line, you're going from, if you say that it's going to 1, you might say that it's coming from 0. That's appropriate. So that point could be considered 0, but we're not going to say that. The reason is that 0 only works on the line. It only works on the line. I proved that. So without going into that, you could prove it to yourself. That'll be your homework. Prove to yourself that anytime you have a distance, you have to have a 0. And a distance is linear. But I artificially said that this is a line going out. It's not a linear line, so it does not necessarily begin at 0. So let's just leave the numbers out. We have a point, and we're not going to say that this is a distance because we can't define it numerically yet. But we are going to say that any one of those rays that goes from the center to the edge can be considered a unit distance, a unit linear distance. And if so, there is an integral to that. At the surface, where the line stops, has an integral that's different for any radius. That the integral changes. You can see it. The sphere gets bigger as the radius increases. There is a direct mathematical relationship between the extending of a single line and the extending of all the lines spherically. That has a constant numeric relationship. And we're going to talk about that when we get to the strict mathematics. That'll be in the next presentation. And this is part of my strategy, and I'm just going to reiterate this because this is important. So you know why I'm leaving off here. It's because of the time constraint. So you may ask, how come I spent so much time not talking about the mathematics? It's because I think you see why. It's to show you the importance of this so that the mathematics will bind with that. I wanted you to see the geometry first. We're now going to attach the metric in a way that nobody ever noticed could be done. And it's extremely profound. That will be in the next presentation. Within a day, I'll release that. But that's 52 minutes. Thank you for your attention to this. I hope you're enticed, perhaps entranced, enthralled, because you want to believe this. Be cautious. You don't want to believe this. I am projecting that. Don't fall for that. Wait for the proof. I've already given you a pretty good start, haven't I? We've compared our beginning with Euclid's to show where they're similar, actually identical, and the importance of that, because that leads to the linear number system. So Euclid, oh baby, we had to begin with Euclid. But now there is a new possibility open to us, and complex numbers actually give the first indication of the possibilities in extending the linear number system to spheric space, because the complex number system is a very good shot at it through the circle. And that's something we can't cover right now, but that wraps up our first of two parts. In the next presentation, it'll be about this long, I suspect, 50 minutes. But it will be the number system that goes with this geometry with a new theorem to match the antipodal theorem, which apparently I discovered, but I find that interesting. But the next theorem to be proved is the bootstrap theorem. It's the bootstrap for physical universal space, which is spherical. We know that now. So I hope you tune in. This is Galactic, bringing you the secrets of the universe. Don't forget, at night, if the skies are clear, take a look. Spend a minute, 5 minutes, but do it. You won't regret it. So I like to give that tip at the end, because night is half the day is night. So we'll be right back.